Combinatorics on Words seminar. Our speaker today is Lucas Moll from Thompson Rivers University, and he's going to speak to us about avoiding abelian and additive powers in rich words.
Yeah, thanks, Narad. Thanks to all the organizers. Thanks for inviting me. And yeah, this is joint work with Jonathan Andrade, who was an undergrad at Thompson Rivers University until last year. And now he's started a master's at University of Victoria, also in British Columbia. We're both in British Columbia. And I'm also going to talk about some earlier work with James and Narad and Jeff. So this will be familiar to people, but an ordinary square is a non-empty word of the form XX. So for example, we have murmur and hotshots. And we're going to be interested in two variations of ordinary squares, right? So an abelian square is a non-empty word of the form XX prime, where X prime is an anagram of X. So they have the same number of every letter. So two examples in English are reappear. You've got REAP and then REAP in a different order. And intestines is another example. INTES and then the same 5 letters in a different order. So those are abelian squares. And then an additive square, which is really what I'll be most interested in, is a word of the form XX prime, where X and X prime have the same length and the same sum. And I should have said a non-empty word of the form XX prime. So for example, you've got this 210201, which is an abelian square. It's also an additive square, right? Every abelian square will be an additive square, as long as you're working over an alphabet where adding the letters makes sense, right? But here, 0312, you got 0 plus 3, which is 3, and 1 plus 2, which is 3. So you've got two words of the same length and the same sum. So that's an additive square. And I chose this example because it's not an abelian square, right? So there's even more additive squares than there are abelian squares, which makes them even harder to avoid. So these squares can be extended to k powers, right? So for example, 011, 101, 110, 011. We've got 4 blocks, each of length 3, and each with 2 ones and a 0. So this is an abelian 4 power. It's also an additive 4 power. And I chose this example because actually over a binary alphabet, the abelian and additive 4 powers or k powers are the same, right? When you just have 2 letters, if they form an additive power, it means that you have the same number of each of those letters in each block. So for binary alphabets, abelian and additive powers are the same. So in this talk, I'm going to focus on words over subsets of the integers. But you could consider additive powers over other alphabets, as long as you have some notion of sum. Okay, so what's known about abelian powers? Well, Decking in 1979 showed that abelian 4 powers are avoidable over the binary alphabet, right? And what this means is that there is an infinite word over the binary alphabet that has no abelian 4 powers as factors, right? So you can go on forever with just 2 letters and never see an abelian 4 power. So abelian 4 powers are avoidable over the binary alphabet, 0, 1. And Decking also showed that abelian cubes are avoidable over the ternary alphabet, 0, 1, 2. And finally, Karenin in 1992 showed that abelian squares are avoidable over four letters, 0, 1, 2, and 3. And all three alphabet sizes are smallest possible. So it's impossible to avoid abelian squares over a three-letter alphabet. And it's impossible to avoid abelian cubes over a binary alphabet. And obviously, it's impossible to avoid abelian four powers over an alphabet with just one letter. So basically, everything is known about the question which powers are avoidable, which abelian powers are avoidable over a fixed alphabet. So then we have additive powers where the picture is not quite complete. So I'm going to again focus on just subsets of the integers. So in 1979, Decking showed that additive four powers are avoidable over 0, 1. And Decking didn't use this terminology, but abelian four powers are exactly the same as additive four powers. So Decking's result for abelian four powers actually can be rephrased this way. And it wasn't until 2014 that Kassane, Curry, Schaefer, and Shallot showed that additive cubes are avoidable over 0, 1, 3, 4. So there's an infinite word over these four letters, 0, 1, 3, 4, that contains no additive cubes as factors, which is a pretty cool result. And then Rao in 2015 basically took the construction of Kassane, Curry, Schaefer, and Shallot and found some maps from that infinite word to smaller alphabets that still had the property that they had no additive cubes. So additive cubes are avoidable over several subsets of the integers of size 3. Not all of them, but several of them. And I didn't mention it. I didn't write it down here, but it's also been shown by Leotard and Rosenfeld that additive cubes are avoidable over every subset of Z of size 4, except possibly those ones that are equivalent to 0, 1, 2, 3. So we're getting close to knowing exactly which alphabets additive cubes are avoidable over, but we're not quite there yet. And it's still an open problem whether additive squares are avoidable over some finite subset of Z. So we still don't know, which is kind of shocking. I would really like to solve this problem, but finding a construction seems really hard. So what has been shown is that additive squares are avoidable over a finite subset of Z squared. So if you are willing to take ordered pairs of integers, then you can avoid additive squares. That was shown by Rao and Rosenfeld. Okay, so that's what's known basically about avoiding abelian and additive powers. And what I'm going to talk about is the same sorts of problems, but for rich words. So to define rich words, we need to talk about palindromes. A palindrome is a finite word that reads the same forwards and backwards, right? So it's equal to its reversal, if you like. So 0, 1, 0, 1, 0, that's a palindrome. Some natural language examples are kayak, and this really long one from Finnish, which everybody uses because it's the longest natural language one, I think, that's known. Anyways, I think it means soapstone seller or something like that. So a theorem from 2001, which really kicked off the study of rich words, is that every word of length n contains at most n distinct non-empty palindromes. And when they proved this in the paper, I think there was some sentence that said basically like yeah, this is easy to prove, but it doesn't seem to have been written down before, right? And the the reason is just that if you add a letter to the end of a word, um, you can create at most one new palindrome, right? I mean, imagine if you created two, well, then the smaller one would have to be at both ends of the bigger one, right? So adding a letter to the end of the word is going to create at most one new palindrome. So if you have a word of length n, it's got to have at most n distinct non-empty palindromes. So if a word of length n has at most n distinct non-empty palindromes, then, well, the words that have the maximum number of palindromes, let's call them rich, right? Shortened from palindrome rich. So a word of length n is called rich if it has n distinct non-empty palindromes, the maximum number of palindromes in a word of length n. So for example, you could imagine building this word 0110, one letter at a time. And when you add the 0, you get a palindrome. When you add the 1, you get a new palindrome. When you add the second 1, you get a third palindrome, 1. When you add the fourth letter, you get a fourth palindrome. And when you add the fifth letter, you get one last palindrome, 101. So this word has 5 distinct palindromes, so it's rich. On the other hand, if you look at 0120, well, it has palindromes 0, 1, and 2, but then when you add the last letter, there's no new palindrome, right? So this word is not rich. It has only 3 palindromes, and it has length 4. Okay, so are there any questions about that or about anything so far? So an infinite word is called rich if all of its finite factors are rich.
So, sorry for stupid question, but every factor of a finite rich word is rich.
That's right. Yes, you can prove that if you have a finite rich word, then all of its factors are rich.
Ah, okay. Thank you.
Yeah, so the language of rich words is factorial. Yeah, anything else? Any other questions? Okay, good. So, like I said, what we were interested in was the same sorts of questions that I showed you the answers to at the beginning for avoiding abelian and additive powers, but now we're going to restrict ourselves to infinite rich words. So what Jonathan and I proved is that there's an infinite additive 5-power free rich word over the binary alphabet. So there's an infinite rich word over 0, 1 that has no additive 5 powers. And we also showed that there is an infinite rich word over 0, 1, 2 that has no additive 4 powers. And these alphabet sizes are the smallest possible, even for abelian powers. So I mean, I stated these results just for additive 5 powers and additive 4 powers. But of course, if you have no additive 5 powers, then you have no abelian 5 powers, right? If you have no additive 4 powers, then you have no abelian 4 powers, right? So in fact, you can show that if you backtrack over 3 letters, then, or sorry, over 2 letters, then you're going to get an abelian 4 power, right? So there you go. And so the question is, I mean, we kind of described the smallest possible alphabets over which you can avoid 5 powers and 4 powers. So what about squares and cubes? So For squares, unfortunately, well, not unfortunately, for squares, we just know that it's not possible, right? For squares, it's been shown by Palantova and Starosta that every infinite rich word over a finite alphabet contains an ordinary square, right? So it must contain an abelian and an additive square, right? And for cubes, we don't know, right? So Jonathan and I tried to find a construction of an infinite additive cube-free rich word over a finite subset of the integers, but we didn't find such a word. We also didn't really. We did some backtracking searches, which of course I don't remember the exact outcomes, but we didn't find any sort of anything really interesting. I think even over like the alphabet 0, 1, 2, 3, our backtracking search didn't end. I could be wrong about that. I could be misremembering, but yeah, we really don't know for additive cube-free rich words. We're really not sure whether such a word exists. Okay, so questions about that? All right. So how did we construct such rich words? Well, we did the usual thing and found some morphisms and iterated them, right? So defined beta from 0, 1 to itself by beta 0 is this and beta 1 is this, and define gamma in this way, right? And we show that the fixed point of beta is rich and additive 5 power free, and that the fixed point of gamma is rich and additive 4 power free. Okay, and I mean, what's sort of special about these morphisms? What sort of allowed us to complete the proof is that when you look at the images of the letters, right, the length and the sum of the images of the letters, they're linear functions of the letters themselves, right? So when you look at beta, the length of beta 0 and beta 1, it's both 5, right? Which is a linear function of the letters, right? It's 5 plus 0 times the letter, right? And the sum is, well, here for beta 0, the sum is 1. For beta 1, the sum is 3. So the sum is like 1 plus 2x, where x is the letter, right? And it's a similar thing over here for gamma. So first of all, the length, 1, 3, 5. So this is a linear function of 0, 1, 2, right? The length here is 1 plus 2x, where x is the letter. And the sum is also a linear function. The sum of each of these images is 2, right? So it's 2 plus 0 times the letter. So that was the property of these morphisms that made the proof of the additive power freeness possible. So first of all, I'll talk about how we proved that the words are rich. So we used the one of the first characterizations of rich words. So an infinite word W is rich if and only if every finite prefix of W has a unit occurrent palindromic suffix. So a palindromic suffix that occurs only once in the word or in that prefix, right? So every prefix of the infinite word has a palindromic suffix that occurs exactly once. So this is exactly kind of how I was describing finite rich words, right? Every prefix you get a new palindromic suffix. So that works for infinite rich words as well. And so using that characterization, we were able to use walnut to show that the binary word is rich. And basically what we had to do was just express this characterization in the first order logic of walnut. So for people that aren't that familiar with walnut, explaining the code sort of step by step won't do much good, but I'll explain a little bit, right? I mean, this is how you define that morphism in walnut, right? You just use this syntax to say 0 goes to 0, 0, 0, 0, 1, and 1 goes to 0, 1, 1, 0, 1. This promote command, it sort of creates an automaton that outputs the sequence capital B, right? And then these last four are just expressing this characterization in first order logic. So I'll go through the last command. It basically says for all n, so for every prefix of length n, there is a j where there's a palindrome starting at index j of length n minus j. So there's a palindrome at the end of our prefix of length n, which does not occur in the prefix of length n minus 1. Right? So basically, you can just express this in walnut using first order logic, and walnut returns true. So in fact, every finite prefix of this infinite word does have a palindromic suffix that occurs only once. So that's what we did for the binary word. For the ternary word, I could be wrong that it's possible to do this using walnut, and I just wasn't clever enough to find the automaton that produces the word gamma. But I'm not sure if gamma is an automatic sequence or not. So what we did was we used an inductive proof with several cases. It's a couple of pages long, but it's not too bad. And we just, again, used this characterization. So that's how we proved richness. Okay, and then most of the rest of the talk will be about how we proved additive power freeness of these words. And we use a recent variation of the template method. So maybe some people are familiar with earlier versions of the template method. So it kind of goes back to this theorem of Curry and Rampersad from 2012. So they proved that there's an algorithm which decides under certain conditions on H whether the fixed point of H contains abelian K powers. Okay. And I'm not going to describe the conditions here, but you can look them up if you need to, or if you're interested. So that was kind of the first decision algorithm for abelian powers. And it used this template method, which had been kind of used in an ad hoc way before. Like the method was working for some reason, but nobody quite knew why. Right? So it was Nerad and James that figured out why it was working in general, and they came up with these conditions that ensured that you only got finitely many templates in the method. So I'll get into that in a bit. So a big development was made by Rao and Rosenfeld, who found much less restrictive conditions for this algorithm, and they adapted it so that it could be used to work for additive powers as well. And so it was in this paper that they proved that there's an infinite word over a finite subset of Z2 that contains no additive squares. Right? And this paper is, they actually proved a lot of interesting results in this paper. Okay, and so the version of the template method that Jonathan and I used was a recent variation due to James and Nerad and Jeff and myself. And it has much more restrictive conditions, and it works only for additive powers, but at least what we found was that it's probably more efficient. I mean, we didn't actually analyze the computational complexity, but basically the whole reason that we discovered this alternate variation is because we tried to apply the earlier algorithms, and it just was taking too long, right? We were getting too many templates, and none of our calculations were finishing. So we sort of modified the approach and made it possible for the algorithm to actually finish. So I'll explain a little bit more about these templates, but the main difference between this 2024 variation and the earlier variations is that in the early variations, they were keeping track of Parikh vectors. So throughout the algorithm, you were keeping track of the number of occurrences of each letter in a word. And for large alphabets, this is like quite a those vectors get big, and there's lots of them, right? On the other hand, we were interested in additive powers, and it turns out that all we needed to keep track of was the length of the word and the sum of the letters in the word. And that was enough information to kind of make the method work for us. So in this 2024 paper, we applied this algorithm to one specific word, but we didn't implement the algorithm in general. So that's what I had. That's what Jonathan was working on when he worked with me in the summer, and he implemented this algorithm from 2024 in general, and it's available on GitHub if anybody wants to use it. So he implemented it in general and then applied it to these two words, beta and gamma. So my plan is to sort of describe this template method to you. So I'm just going to check my time for some reason. Okay. Good. For some reason, I can't see the clock on my computer. Must be a sign that I'm getting old. Anyways, so the template method. Let's talk about this. So the result is that there's an algorithm which decides under certain conditions on H whether the fixed point of H contains additive K powers, right? And the essential idea is this, that any long additive power in the fixed point must have arisen by applying H repeatedly to some short seed word, right? So if we have a long additive power, then it must have come from something short that we applied H to, right? And the idea is to show that these seed words aren't too different from additive powers, right? So they look almost like additive powers, okay? And what we prove is that there's only finitely many templates for these seed words, right? So there's only finitely many forms for these short seed words. And once you find all of the templates, you can just enumerate all of the short words in your fixed point and check to see if they match any of the templates, right? And either you get a match, and that means that your word has an additive power, or you don't get a match and your word is additive power free. So some obvious questions are, what are the conditions, right? I haven't told you what the conditions are. And how do we describe these seed words, right? So I'm going to sort of explain, or hopefully sort of give you rough answers to these questions by giving you just a sketch of how this works. So for simplicity, I'm just going to focus on additive squares. It just makes it easier to visualize what's going on. But of course, the same ideas work for larger powers. So what's a template? Well, a template is it's a form that's similar to an additive square, right? So in order to define it, we first introduce this vector. Sigma of W denotes the vector with the length of W and the sum of W, right? So this replaces the Parikh vector from earlier template methods. And a template for additive squares is a 4-tuple starting with 3 letters, right? Letters or the empty word, and ending with a vector, which is going to basically be something involving these sigmas, right? So it's going to be a vector where the first entry is a length and the second entry is a sum. And a word W is an instance of this template, right? So the template is describing the form. So a word is actually an instance of this form. If W looks like, well, we've got the 3 letters or epsilon, A0, A1, A2. And then we've got 2 words, W0, W1, where the difference between the length and the sum of those 2 blocks is our vector D. Okay. So in particular, what this means is that if we have an instance of epsilon, 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 0, well, that's an additive square. We have epsilon, 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 and 2 blocks, W0, W1, where the difference between their length and their sum is 0, right? So epsilon, 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 0 describes additive squares, right? And just as another example, an instance of this template, 0, 1, 0, 1, 3, is not too far from an additive square, right? It's close to an additive square. The word would look like, well, we'd have a 0, a 1, and a 0. And then we'd have 2 blocks, W0 and W1, where the difference between their lengths is only 1, and the difference between their sums is only 3, right? So this is pretty close to an additive square. Okay, so hopefully that makes sense. Please let me know if there are any questions. So the idea is that every long enough instance of a template must have come from an instance of another template. So every long enough instance of a template has a parent template, right? So basically, if you have at the bottom here a template that you're interested in, say a template for additive squares, right? Then, well, it must have come from some shorter instance of a template by just applying H, right? I mean, the picture must look something like this, right? The letter A0 must be sitting in the image of some letter or epsilon, right? The letter or epsilon A1 must be sitting in the image of some capital A1, and A2 must be sitting in the image of some capital A2, right? And then W0 and W1 might have a bit of overlap with the images of big A0, big A1, and big A2, but they're mostly coming from big W0 and big W1, right? So every long enough instance of a template must have come from a parent, right? And so the first two conditions that we need is that the morphism H is affine. So this is basically what I was describing before about beta and gamma. It's that the length and the sum of the image of each letter, they're just linear functions of the letters. So let me sort of give you an example, right? So beta 0 is 0, 0, 0, 1, and beta 1 is 0, 1, 1, 0, 1. So the length of each of these letters is just 5 plus 0 times the letter, right? So we put 5 and 0 in this matrix, right? And the sum of each of these images is 1 plus 2 times the letter, right? 1 plus 2 times 0 gives us 1, and 1 plus 2 times 1 gives us 3. So we put 1 and 2 here, right? So this condition just basically makes it easy to tell what sigma is when you apply H, right? Basically, you can when you apply H to a word W and want to know the length and the sum of that image, well, just take the length and the sum of the word you started with and multiply by the matrix MH, right? So there's a similar result for Parikh vectors and the incidence matrix, right? But this affine condition makes it work, even if you only know the length and the sum. Okay, so that's condition 1, and condition 2 is that this matrix is invertible, right? And basically that just allows us to sort of take pre-images, right? So let me show you the picture. Basically, these first two conditions allow us to find all the possible parents of a given template. So say you have this template and you want to know where it came from. You want to know what sorts of words could have mapped to this word. Well, first of all, there's only finitely many choices for what big A0, big A1, and big A2 could be, because your alphabet is finite. And there's also only sort of finitely many ways you could position these blocks, right? Because the length of each image of a letter is finite, right? And then once you sort of position those blocks, well, the W0 and W1 are kind of determined, right? Because you can just take the inverse of H and figure out what W0 and W1 and have to be, right? So anyways, what I'm really trying to say here is that if you start with a difference, if you start with a template A0, A1, A2, D, right? Then you can figure out what big A0, big A1, big A2 could possibly be. And then the conditions on the matrix also allow you to figure out what the difference big D is going to be, right? Basically, the difference between these W0 and W1 is completely determined by the way you choose the big AIs and the way you choose their positions and the difference that you started with. So that's a very rough sketch with a lot of hand waving, but basically these first two conditions allow you to find all possible parents of a given template. So they allow you to find all possible forms from which your instance of a template may have come from. Okay, and so now that you can compute the parents of a given template, we want to compute the set of all ancestors of that template, so the parents and the grandparents and so on. So the question is, how do we know that this set is finite, right? Because, I mean, conceivably, it could just go on forever, right? You could have lots of parents, lots of grandparents. It could keep going. But what we need is a condition which tells us that for any ancestor, this difference, big D, is not too large, right? And one condition that works is that the eigenvalues of the matrix are larger than 1 in absolute value. And the reason that this works is because it means that when you apply H, you're kind of blowing up differences. You're kind of blowing things up. So you're blowing up differences in the lengths and the sums. And so if you start with a big difference, it's going to get worse, right? Right. So basically, this condition ensures that there's only finitely many possible vectors that big D, could take on if it's an ancestor of a fixed template. Okay, and then the last condition is just that H is strictly growing. So the image of every letter has length at least 2. And this condition could probably be weakened, but I won't talk about that. Basically, this just means that taking pre-images makes words shorter, right? So if the fixed point contains an instance of a template T, then it actually contains a short instance of some ancestor of T, because you start with your instance of your template, you take its parents, right? But when you do that, you're making the word shorter at every step. So if you have a long instance, just take pre-images until you get a short instance of some ancestor. So basically, if you have a morphism H that satisfies these 4 conditions, then you look at the template for an additive square. So we've got 3 letters epsilon, two blocks W0 and W1 with difference in their lengths and sums being 0. So an instance of this template is an additive square. We enumerate all of the parents, all of the grandparents, right? Until basically our set closes off, right? We know there's only finitely many choices for this vector in our ancestors, and there's only finitely many choices for these letters or epsilon, right? So there's only finitely many possible ancestors. So eventually we'll find them all if we just keep taking parents. And if the fixed point contains an additive square, then it must contain a short instance of one of these ancestors. So those are what our potential seed words are. And so all we do is enumerate all the short factors of the word and check to see if any of them matches an ancestor template. And if we do find a match, well, then applying H repeatedly to that instance will eventually give us an additive square, right? So that would tell us that the fixed point is not additive square free. But if not, if there's no such short seed word, then this word is additive square free. So that was very, very quick, but hopefully it gives you some idea of what the conditions are and sort of the objects that we're dealing with here. And the nice thing about this algorithm is that we're able to implement it in general. Like there's no sort of worry about floating point error or anything like that. It's a pretty simple algorithm to implement. So I'll just give you some problems to work on here. So first one, is there an infinite additive square free word over some finite subset of Z? So, I mean, one of the reasons that I put so much work into this new variation of the template method is because I think it's more efficient than the other one, and if we do find a huge morphism that seems to produce additive square free words, we'll probably need a fairly fast algorithm to actually prove that it's additive square free. The other reason why I think this might actually be helpful in some way, the more restrictive conditions, is that when you have more restrictive conditions, you can sort of shrink your search space artificially, right? And sometimes that allows you to find something faster. So if everybody could just start searching for morphisms that meet our conditions and seem to produce additive square free words, that would be great. So that's the first open problem. Just find an infinite additive square free word over some finite subset of Z. I mean, we know that that's not possible for rich words, but we're not talking rich words here. So there are some questions for rich words still, though. So is there an infinite additive cube free rich word over some finite subset of Z? We don't know that. And finally, is there an infinite additive 4 power free rich word over every subset of Z of size 3? So we showed that over the set 0, 1, 2, there's an infinite additive 4 power free rich word. And it actually seems like if you replace the letters 0, 1, and 2 with some other subsets of size 3, this word is still additive 4 power free. So it's possible that this problem is not as hard as it might seem, because maybe you just have to take our word and show that replacing the letters 0, 1, and 2 with any 3 distinct letters will work. But we haven't shown that yet. So yeah, that's all that I wanted to talk to you about.
Oh, thanks a lot, Lucas. Does anyone have any questions for Lucas? Yeah, Hajime.
Thank you for nice talk. I have a question about related to the last open question.
Okay.
So is it possible? So in the case where alphabet is not 0, 1, 2, so is it possible to find a certain substitution, so generalized of your talk, so generalization of beta and gamma?
Yeah, I mean,
for certain case.
It's possible that if you just take gamma and apply a coding, so just swap 0, 1, and 2 for, say, 0, 1, and 3. It seems like that word is still additive 4 power free. And it'll still be rich, because richness doesn't depend on what the letters are, right? Richness, we don't care what the letters are as long as they're distinct. So that is possible, and I haven't proved it. So that is the way Leotard and Rosenfeld, they proved that additive cubes are avoidable over every subset of Z of size 4, except possibly 0, 1, 2, 3. And that's basically what they did, is they found a few constructions and then applied these codings, just swapped the letters one by one, and that worked. So maybe their methods would work here as well.
Thank you.
Jeff.
Yeah, hi. So a couple questions. I guess the first one is, suppose you have a morphism which you believe has some nice properties, but you don't know the right weighting of the letters. Let's say even a uniform morphism. Is there some nice way to check reasonable possible weightings?
I think probably. I think that NARAD came up with a way that I think if you look at the incidence matrix, then one of the eigenvectors will give you the weightings. I'd have to double check, but Nara, do you remember?
I remember coming up with that, but I don't remember specifically. But I think that's right. I think it's yeah. I'll have to look in my emails to find that. But yeah, it's some condition like that. It might be the second eigenvector or something like this that gives you the weights. But yeah, I'll have to go back and check my emails to remember again the exact um, condition to how to get those weights.
Okay.
Yeah, but I
Eh,
think basically the answer, Jeff, is yes, that if you have a morphism and you're just looking for the weights, you can do it.
Okay. And the other question was how long did this program, your students program take on, is it verifying these things in seconds or minutes or hours or
Yeah, so
just
for beta and gamma, I think it was under a minute for both of them.
oh nice.
For some longer morphisms, it was taking maybe an hour or a couple of hours. Like we applied it to maybe a 25 uniform morphism that was just an old one that James had found. And it finished after a couple of hours.
Nice.
And I think that was for additive 4 powers. So, that seems to be the problem, is when you want to use this for higher powers, it just means that the number of templates gets so much bigger because you have so many possible letters and so many possible vectors, right? You have to keep track of the differences between 4 blocks instead of just the differences between 2.
Thanks.
Are there any other questions? All right. If not, thanks again, Lucas,